Good afternoon. Welcome to lecture 31 on thermodynamics of material. So today if you have any questions, I can answer. Okay, before your test. Do you have any questions? Preparatory question, or I can move on then. So second law of thermodynamics. So today topic is the second law of thermodynamics. Then and entropy. So we actually consider one or two reversible cycle. Let us see. We'll consider first a reversible cycle. So we'll let us consider a reversible cycle. Reversible cycle with n moles of ideal gas as system, as a system. This we consider, and also this let us consider this cycle is comprised of isothermal and adiabatic processes. Considered in turn one after the other. Is okay? In turn, with expansion and with expansions followed by compressions. So this is the cycle. Let us do this, consider this. Now the PV diagram. Happy? So we consider this cycle isothermal, adiabatic, So 1, 2, 3, 4. This is the cycle. So, this is isothermal, this is adiabatic. Okay. So this is isothermal. What is the temperature? T1. This is the isothermal. Temperature T2. Note here T1 is greater than T2. Okay, this is adiabatic. This is also adiabatic. One, two, three, four, one cycle. First we consider, for some reasons, I will not reveal it now. For some reasons I consider this. Okay. Step 1 to 2. We consider something, consider this step 1 to 2, integration dq reversible by t. We consider these functions dq reversible by t for some reasons. Okay. Over 1 to 2. What is this? What is this step? You know very well, right? Isothermal expansion. As you see clearly, isothermal expansion. So write that character. At the end, I will tell you why I consider this function dq reversible by t. Is what this? Tell me. Is what 1 to 2 dq reversible? You know, du plus dw reversible by t. And since isothermal, you know, du is 0. Sorry, I'm very sorry. Ideal gas, so ideal gas and isothermal. Ideal gas and isothermal, dw reversible is what? And this is nothing but, you know, PdV. dw reversible always PdV. So P by T, so it is actually 1 to 2. P by T is nR by V. So nR dV by V. Just check this. Checked is what? nR ln V2 by V1. Okay. See, this is the V2 by V1. Okay, you can assign here. State 1 is what? P1 V1 T1. State 2 is what? P2 V2 T1. In adiabatic, P3 V3 T2, and the last one is P4 V4, and back to temperature T1. So these are the things. Okay, quickly. So this is, you may note this V2 is actually, this is, you know, this is positive. Next is step 2 to 3. Step 2 to 3 is what? Adiabatic expansion. Integration dq reversible by t 2 to 3 is what, you know, adiabatic. No, so it is 0. Next step 3 to 1, 3 to 4. Step 3 to 4, similarly, it is what? Isothermal compression. dq reversible by t is as before is what? As before is what? 3 to 4 nr dv by v as before. Okay, as before, you may write. For isothermal is what? nr ln v4 by v3. This is of course a negative quantity, as you see, V4 by V3. I made a mistake. V4, yes, right, correct. V4 is, okay, smaller volume. This is larger volume. V4 by V3 is a compression. Come on in. V4 by V3 is negative. Last is next step 4 to 1 is adiabatic compression. Again you write similarly dq reversible by t 4 to 1. You know, 4 to 1 is what? dq reversible by t as before 0. 0. So now you do what? You just when I remove this I remove this right, this I remove, make some room. So this I remove. Okay. So now what I do? Get this integration. Now I consider integration dq reversible by t over the cycle. This is a cycle. Cyclic integration, you know, cycle is what? What you will get? Just sum them. Sum them. Integration dq reversible by 1 to 2 plus dq reversible by t 2 to 3 plus integration dq reversible by t 3 to 4, you know, cycle. Integration over the cycle. Over the cycle. Or the cycle 1, 2, 3, 4, 1 over the cycle. And last is 4 to 1 plus 4 to 1 dq reversible by t. Now in a position to write this, copy this down term by term. I am removing this part only I am removing. Okay. So I get this first one is as you see, first one is nr ln v2 by v1. So substitute this nr ln v2 by v1. Okay, first one I copied. Second one is 0. Third one is here. Can I remove this? nr ln v4 by v3. nr ln v4 by v3 plus again last one is 0. So you have these results. So I remove all these things now. Zero. So what it is? Write another line in case you want to. Write the two terms. Now note, we want to get a relation between, see, V2 by V1, V2 by V1 and or V3 by V4, perhaps there's a linkage. V2 by V1 and V3 by V4 may be equal, but let us establish this. Consider for this to next. Okay, let us consider here separately. Let us consider to get the relation between V2 by V1. To get the relation between V2 by V1 and V4 by V3 and V4 by V3. V4 by V3. Okay, this is. So what is it? Consider adiabatic 2 to 3. Consider the reversible adiabatic. Consider the adiabatic path 2 to 3. What is the relation? You know, reversible adiabatic. So you will apply this T1, Tb to the power gamma minus 1, Tb power gamma minus 1 is constant. Apply that. T1 V2 power gamma minus 1 is T2 V3 power gamma minus 1. Leave it in this form. Okay. And so you can write here, or T1 by T2 is how much? V3 by V2 power gamma minus 1. Again consider the other adiabatic. The adiabatic path 4 to 1. Path 4 to 1. Another second adiabatic. What you get again? Apply here T1 Tb to the power gamma minus 1, T1 V4 to the power gamma minus 1 is Tell me, is what is adiabatic? T1, T2. So what should be there? So I made a mistake somewhere. Or this is isothermal. Recall. This is isothermal. Hello. What I wrote here? What I wrote here? Just oh. P3, V3. Wait a bit. V4 is okay. This is T2. What I wrote here previously, adiabatic isothermal. Okay, anyway. Okay. Hello. Okay, no amusement. Okay, here. Okay. You may get back here. You may sit back there. You. Okay. You sit back there. He first, then later on maybe you. Okay. You go. So what? Sorry. T2 here. I'm very sorry. T2. V4 to the power is a C T2. This is isothermal T2. Okay. T2. So please correct this. This is T2. Okay. T2 V4 power gamma minus 1, and then it is T1 V1 power, what is this, gamma minus 1. So this leads to what? Tell me. T1 by T2 again. Find T1 by T2. 1 you get V4 over V3 V1 power gamma minus 1. So from these two, so call it say 1, 2, from 1 and 2, from 1 and 2, what you get? This left hand side same, right hand side same. V3 by V2 is V4 by V1. Right hand side have actually power gamma minus 1 in each case, so cancel out. So this is one way of writing this. But since what relation V2 by V1 is V4 by V3, so or you write here, or V2 by V1 is what? V2 by V1 is V3 by V4. This you arrived at. This is the relation you got. You apply this here. V2 by V1 is V3 by V4. So V2 by V1 is what? This is, oh right, another line. Sorry. Keep it there intact. So NR ln V3 by V4 plus NR ln V4 by V3 is how much? You know, this log x plus log 1 by x is how much? Hey, hello, log x plus log 1 by x, how much? Log x plus log 1 by x. 0. So here, what it will be here? These two. Okay. So this is 0. So log x is minus log 1 by x. Minus log. So it is minus. This is V4 by V3 is V3 by V4. Then it will be minus. Minus plus. Minus plus is what? Is okay. So this is like this. NR ln V3 by V4, and since log NR ln V3 by V4 is 0. This is the fantastic observation. So remove this, sorry, this you remove, these are, so this line the outcome is what? Conclusion, observation, okay. So observation, okay, observation maybe, just we are trying something, observation or conclusion. Integration dq reversible by t cyclic is 0 from the first cycle. This is our finding so far. Now, very interesting thing. Cyclic integration of this is 0. Very interesting. Okay. Normally, we know about this thing happens where, in which case, cyclic integration of something is 0. What is that? Internality or any state function, maybe d of a state function. So we'll take up this. So can I remove this part? What is okay? One cycle is over. You may think that this applies only for this special type of cycle. This special type of cycle, there is a name to this. Isothermal adiabatic, it is Carnot cycle. Okay, but don't worry about this. Okay, as if we don't know, we are actually starting from the very beginning and we are trying to explore ourselves what happens. we consider this. So we change the cycle. Second cycle we consider next. So I'm removing all these things. All these things. The observation I have written there. So second cycle. Let us consider a second cycle. Let us consider as if we are not very convinced that this will be always 0 or any cycle. So let us try another cycle. If that works, let us consider if that also gives the same results. Okay, let us consider. Let us now consider another reversible. This is the constant pressure, comprising constant pressure and constant volume in turn with heating and cooling. Okay, with heating and cooling. What is your name? What is your name? You are Abhay na to Abhay. Okay. Your name is what? Oh, Haripal Prasad. Okay. Roll number beginning. Roll number. Okay. This first day or second day? You're here? Visit here? Many. Okay. I have the attendance sheet here. 9 to 10 classes. Oh, 9 out of 31 running. And you, how many? 3 to 4. 3 to 4. Good. 1/10. So, with heating and cooling. With alternate, okay, in turn with heating followed by coolings. Cooling. Okay, let us see, follow this. I am drawing this sketch. What is the sketch like? You can draw yourself, PV diagram, always. System has not changed, n moles of ideal gas, okay? Again, system still remains same, n moles ideal gas. Happy? Okay, draw this cycle, PV diagram. First I draw 1 constant pressure, 1 to 2, then constant volume, 2 to 3, then constant pressure back, 3 to 4, and 4 to 1. 4 to 1. Okay? So, this is our cycle. Constant pressure, constant volume type cycle. Okay? 1, 2, 3. What is the assigned here? What is the state? P1, V1, T1. State initial P1. Then next would be, since constant pressure cannot change, P1, but volume must, V2, and temperature change. Hello, Sachidananda. Yeah. Second is again constant pressure, P1, volume is same, sir, V2, temperature is again changed, and last is pressure same, P1, volume is back to V1, temperature has changed, because you consider why temperature has changed, you see, here pressure constant, volume has increased, so temperature has increased. Again here, which is pressure is, volume is unchanged. Oh, pressure is what? This is P1, this is P2 pressure. So what I was saying, you are thinking this, okay? This is volume fixed, so pressure is P2, pressure is P2, and this is likewise P2. This is pressure P2, what? Pressure has fallen, so temperature has fallen. Then it is what? Next is constant pressure, pressure unchanged, volume has decreased, so is temperature. So first step, like last time, step 1 to 2 we consider. What we consider? Integration dq reversible by t. Stepwise, then we will add them together to get the cycle. We will change for the cycle. What is this step you write? Constant, you want to write, okay, specify this constant, describe constant pressure. What is this? Temperature has volume means heating, constant pressure heating. You write this, you may not write, but constant pressure. This is what? Complete this. dq reversible 1 to 2, you know. What is constant pressure? dq reversible is what? Ncp dt. Tomorrow your test. Remember 10 to 11 though. Okay, you come in time. Remember, I will tell you. 10 to 11 because you have lab now after this. Okay, so you should be okay in time so that actually on time so that I can leave you also in time. Okay, maybe 5 to 10 minutes. Be careful in that. I have already given details. Ask. So Ncp dt by tt is what? Ncp ln t2 by t1. Happy? Happy. Okay, first step. Step 2 to 3. What is this step? Take a look. Constant volume. Constant volume. Achha, right? Constant pressure here, constant P, constant volume. Constant volume, what? This is cooling. Follow? This is cooling because pressure has fallen means temperature has fallen, like this. Okay. So, so this, okay, is what I can write. dq reversible by t quickly. Very quickly, 1 to 2 is what? N Cv dt by t. 2 to 1, oh sorry, 2 to 3. 2 to 3. 2 to 3 is what? N Cv ln. This is constant volume, you know. dq is what? In constant volume, N Cv dt. In constant pressure, N Cp dt. Okay. See? So nothing new, okay. Is all well known to you. So step 3 to 4 is what? Tell me what process? Step 3 to 4. Constant pressure, heating or cooling. Take a look. Constant pressure. See, this is what has happened. Pressure is constant, volume has happened, volume decreased. So is temperature. So cooling, that means cooling. Constant pressure cooling. What is integration dq reversible by t? 3 to 4 is again 3 to 4 n. This is constant pressure again back to Ncp. Ncp dt by t is Ncp ln T4 by T3. Last is step 4 to 1. Okay. Step 4 to 1. Constant, what is, write this? 4 to 1 is a constant volume process. Take a look. Constant volume what? Cooling or heating? Heating. Because pressure has increased, so is temperature. So you write this dq reversible by t. 4 to 1 is 4 to 1 n, since it is a constant volume, n Cv dt by t, you get n Cv ln T1 by T4. That's it. So let for the over the cycle, we will try to find out over the cycle, and let me write. Hence, cyclic integration of dq reversible by t, like last time, exactly like last time. Is what? Add the steps dq reversible by t for each steps and add them together. Step 1 to 2 plus dq reversible by t. 2 to 3 plus dq reversible by t. 3 to 4 plus, this is V, remember, P, this is P, arrow, okay. 3 to 4 plus what? Plus dq reversible by t. 4 to 1. Just substitute your results from here, this side, Ncp ln T2 by T1. You clearly see. Next, Ncv ln T3 by T2 plus Ncp NCP ln T4 by T3. And last term is what? NCB ln T1 by T4. This is your result. Next, so I remove this side. I remove all these things. Okay, left hand side, all. I copied this. So, right? Okay. So remove this side. Next is what we will do? Tell me. So we want to connection between see T1, T2, T3, T4, etc. Next, to find a relation between T2 and T1, relation between the temperature ratios. Well, temperature ratios we consider what we consider? We consider follow path 1 to 2. Consider path 1 to 2, which is a constant pressure path. You know, if pressure is constant, see, then volume and temperature has a proportional relation. So what we get, since constant pressure is a constant pressure path. So what you get out of this is V1 by T1. You can very easily write this, or V1 by T1, or rather V1 by V2, rather you write V1 by V2 is T1 by T2. Do you have any difficulty? No difficulty. You know, V1 by V2 is T1 by T2. Since pressure is constant. Similarly, consider what path? Tell me, guess. 3 to 4. 3 to 4 you can consider. Again, constant pressure. Path. What is this? You write, tell me. You see pressure constants again. V1 by V2, right? V1 by V2 is nothing but T4 by T3. You all set? All set. Give it 1 and give it 2. This is 1. Sorry. So from 1 and 2, what you get? From 1 and 2, you get what? Tell me V1 by V2 left hand side. So T1 by T2 is T4 by T3. So T1 by T2, T4 by T3 here, and T1 by T2. So to make it is T2 by T1, make it T1 by T2, then it will minus. This minus or this plus cancel. 0, 0. Similarly, but this, what it is this, sir? T1 by T1 by T4, okay? This is, okay. Then you can get also, and you get T1 by T, or T1 by T4 is T2 by T3 and likewise. So these are these or this. So if you use this for the next one, T1 by T4 is T2 by T3. So this is T2 by T3 and this is T3 by T2. Otherwise same, NCB, T1 by T4, T3 by T2. T1 by T4 is T2 by T3 and this is T3 by T, opposite, inverse. Log inverse means they cancel out. So this you get what? So again same observation. So we change the cycle, but result is, or observation is the same. What is the observation? So in each case, so in each cycle, each of the two cycles consider. So cycles considered, we have this very interesting observation, dq reversible by t is 0. Actually, for any cycle this can be shown. Actually, this relation can be found, this result can be found with any cycle. Constant pressure, adiabatic, constant pressure, adiabatic. constant volume isothermal, constant volume isothermal, any combination you want, this result can be found with any cycle. Now take up. So we have an interesting observation. Remove all these things all over. Start from here. So what does it mean? Cyclic now interpret this observation. Interpret. Cyclic integration of dq reversible by t is 0. What we learned before? What we learned? We learned before that. We learned before that the cyclic integration of a integration df is 0. And before that the cyclic integration is 0 when f is a state function, not path function. When f is a state function. So what is the conclusion then immediate? This means hence dq reversible by t must be d of a state function. Obviously, cyclic integration of df is 0, and this is cyclic integration of this is 0. So it must be d of a state function. Which function I do not know. This is a new state function. Just now found. Just now. What is the name of this new state function? Entropy. This new state function is named entropy. Entropy. Symbol is of the system. Of the system. Entropy of the system, okay? Of the system. So entropy. So what it is then? Then shall I write ds? This is how we are getting the definition of entropy. What is the definition? It is such a function that ds is dq reversible by t. Oh yes, sir. Okay. I'm very sorry. Here wrong. Okay. This is a cyclic integration of d, and cyclic in this. That means this is analogous to this. Follow. Compare. This is so this part cyclic integration both. So this and this same. So dq reversible by t. I'm very sorry. Is df or a new state function. So this new state function is named entropy, is known entropy of the system is ds. So this is our final. So we remove this. So we start with this. ds hence thus again. So ds is dq reversible by t. This is the definition of the state function. This is the ds is dq reversible by t. And entropy is a state function. A new state function obtained. You have read about many state functions. Enthalpy, internal energy, pressure, volume, temperature. So it's new. Added with the second law. Okay, second law is actually I will give you the exact statement. So this is entropy is the state function. So ds is dq reversible by t. So this is the definition of entropy. This is the definition of. So what is entropy, sir? This is the definition. This much we can say from classical thermodynamics. This is the definition of entropy. in terms of change, not absolute. ds, such a function, entropy is such a function that that the ds is dq reversible divided by t. This is the definition. Okay, this is the definition of entropy in terms of, tell me, in terms of its change. The ds, that is ds. As ds you get, as ds, as given by classical thermodynamics, as obtained from the classical thermodynamics. From the classical thermodynamics. To get absolute definition of entropy, S is what? S is what? To get the absolute definition of entropy, absolute definition of entropy, we will turn to statistical thermodynamics. Hey, hello, you are doing what? Huh?
Sir, someone eat and keep here.
Okay, so you go back there and play with that. Okay, this is okay. Go back there. Go back there. That is a good thing. Yeah. Go back there. Go back there and explore who has actually got this thing. Last bin, and you also go to the last bin. Okay. We'll turn to the statistical thermodynamics. Go to the last bench. Statistical thermodynamics. Which we'll discuss later. Which we'll discuss later. S will be given. Okay. So, we'll discuss later. Okay. Very good. Okay. So this part. Next start. Now we are with this. Now start here. Now next. We consider this. Next, note this. DS system. DS system is what? Follow. This is DS means DS system. S DT system, sir. T system. DP P system. DS system. So I am writing is dq reversible by T. That is again dq reversible by T system. So T means T system. Whose else? T system. DS surrounding we introduce now. DS surroundings. DS surroundings is what? Remember, minus. When system absorbs heat, that means surrounding rejects that heat. Surrounding gives that heat. So it itself loses. So opposite sign always. If it gains, it loses. If it loses, it gains. So opposite sign. So is what? Minus. That's why minus. Opposite sign. Minus dq, but I will not write reversible here. Surrounding will be for, I write something else. Process over this T system, but I will write here T surrounding. This is the, you just box this, box the whole thing, whole bunch. Very important. So DS system and DS surrounding. See why? What does it mean? DS system. This definition dq reversible by T system applicable to irreversible process also. How you get dq ds system irreversible? You will say that this is the answer. State property, sir. Okay, this you follow. I'll take example. Follow this. this you follow, dq reversible is added. But for irreversible, okay, remember, entropy is a state property. So, okay. Okay, this is the okay. So you follow this dq reversible. This is the okay. This is negative sign, opposite sign, because this is opposite sign system and surrounding will be opposite sign. Okay, and this is the temperature of the surrounding dq process. Okay, this is okay. So, acha right here. This relation for DS system is valid for both, not only reversible, since it is tagged reversible, not only for both reversible and irreversible processes. See, I will get some examples, okay? And this is dq process by T surroundings, okay? This is because this is, but this is not. Here process means, right? Here process means actual process. Process means actual process. That is, actually, that is reversible or irreversible, as the case may be. You follow this. Suppose irreversible you are considering, follow me. Irreversible process. DS system is what you will answer? Sir, this process is irreversible. The answer is dq reversible by T system, it cannot be changed. But how will you get that? Well, you shall connect with the reversible between same initial and same final and get this value with the reversible and apply it for the irreversible, because entropy is a state property. Does not matter. For system, reversible or irreversible, you consider. But you don't write ever dq irreversible. Don't write. This is the definition. We see, we went through this. Okay, this conclusion went through these steps and derivations. So never. Process is how, okay, you'll see irreversible. You find it out for a reversible path connecting between the same initial and same final and copy it back into this for the irreversible. But here, no. Here what are? It is process. It is not reversible. Process. If it is reversible, write reversible. If it is irreversible, write irreversible. What this surrounding? Entropy is a state property that we apply for system, not for surrounding. Surrounding has not the same status as system. System is system. Surrounding the remaining part of the universe. See, it doesn't have the same status. See, it follows this. Okay, then number. Now I'll give you these things. Okay, follow this. Now, formulation of the second law. This is very. Now, next, I'm formulating. Next, take up the formulation of the second law. How will you formulate of the second law? You follow this. Follow this. Next step. Follow. I'm writing something. Follow this. Reversible. Reversible process. I'm announcing this beforehand. A reversible process I'm considering. A reversible process. Okay. Then what I'm writing? You see, I'm writing DS system for a reversible process. Right here for a reversible process. I consider an irreversible. Next, reversible. DS system is what? Right nicely. dq reversible by T means T system, as I have already shown you. T system. Okay, happy? Is, I'm writing something, is minus dq reversible by T surrounding. Will you buy this? Check this. Minus plus dq reversible, numerator, okay. T system and C surrounding, you know, they are same. Why? It's a reversible process. In any reversible process, surrounding and system temperature cannot differ more than by dt. Means we say essentially same result. For irreversible, finitely different, finite driving force, infinitesimal. So these two. So write note for a reversible path process, T system is T surrounding. Okay, if it differs actually is T surrounding or say T surrounding. Okay, T surrounding. Okay, for a reversible, because T surroundings for dt, or you can write or is T surrounding plus dt. That is negligible, so it is back to is T surrounding. T surrounding plus dt. Okay, so for reverse, it is isothermal exactly same. Isothermal exactly same. Only when it is constant pressure, constant volume, they change, but dt. So same. If I have written correctly, then write this you give in a comments box. Then from here is continue here. Okay, here you write here is minus. What is this? Follow this side. Follow. What is that? dq reversible by T surrounding. See, process, actual process, reversible. So it is reversible this time. Since we are considering a reversible process. So ds surrounding is minus dq reversible by T surrounding. Exactly what I have written there. So it is minus ds surrounding. It is nothing but minus ds surrounding. So or side change, ds system plus ds surroundings is 0, and system surrounding together constitute universe, or dSUniverse is 0 is the statement of the second law when it comes to reversible process. And I will give a general relationship that applies to reversible and irreversible both, or applies to reversible and irreversible. So this much, this is the second law statement, but I will have not completed the statement. Next I shall do what you can guess, for a reversible process, for irreversible, alongside. This side, for an irreversible process. Then it will be completed. What is the right start? Again, similarly, ds system, right? With me, ds system. What you write? Tell me, as you know, it cannot be different. Peace, always, forever, whole life. Any path, reversible, you don't care. I'll give the application to this for this. Okay, for this later on. But you follow today, you just formulate this at this for today. Tell me, right? dq reversible by T system. Now there is an interesting observation that I tell you. I will give you with examples. But this is very interesting. This I can show here. Okay, is this dq reversible by T system is always greater than dq irreversible by T surrounding. It is very interesting observation. Always you can check actually. This I will take up. I will show you why this happens. I can very easily show you. Suppose isothermal process. Suppose that's for easy explaining. T system is T surrounding, but we know dq reversible is greater than dq irreversible. Isothermal gas expansion. But dw reversible is greater than dw irreversible. So is dq reversible greater than dq irreversible, because internal energy change is same for 1 to 2. So dw reversible greater than irreversible. dw reversible is greater than dw irreversible in isothermal gas expansion. So is dq reversible. So clear. Similarly, constant pressure you can consider, constant volume you can consider, but this is a general thing. Okay. Then is what I'm writing is greater than, I'm writing minus, again that trick, minus dq irreversible. That is okay, continue. That is dq irreversible. I'm very sorry. Irreversible by T surrounding. Happy? Minus minus plus is greater than, can anyone tell me what is this? What is this? Minus in bracket, minus dqreversibility surroundings is what? Note that this is an irreversible process. Or this is an irreversible process. What is this? You don't see dqreversible, see here, the surrounding process is a minus dq process. Process is the actual, I wrote there. The process actual path. This is not actual, always reversible. Connect with the, your path is irreversible, process is irreversible, problem is irreversible, but connect with the reversible. Get dq reversible anyhow between the same initial and same final. But here this is not a question. It's actual, real. Okay, minus dq, so what have we written? Since the irreversible, what is the process? Irreversible process. And this I have written there. That means what is this thing? In bracket is what? What is this? ds surrounding. So greater than minus ds surrounding or ds system plus ds surrounding, sorry, is greater than 0. Side change to naki? Greater than, or ds universe greater than 0. This is fantastic observation. In one case is 0, another case greater than 0, and this is verily the second law of thermodynamics. So shall I remove this? Remove, since we are actually almost running out of time. So in short, I am writing this, you understand, is ds universe in terms of universe, but you have them as well. dSUniverse is what? Greater than equal to 0. Will you be happy? One is 0, another is greater than 0. Greater than applies to what? Greater than applies to inequality. Inequality applies to, tell me, to irreversible process. To the irreversible process. To an irreversible process, irreversible or synonymous is spontaneous. Sorry, irreversible synonymous or spontaneous. Ore Baba, the momentum it was doing well. Spontaneous process. What and equals to is what? This and this applies to, and equal sign is applies to, tell me, applies to what? Applies to a, is it equals to 0 or reversible? To a reversible process, reversible, or what is the other name? Yes, continuous, equilibrium. Reversible is actually through equilibrium, infinite, okay? Passing through equilibrium, infinite number. So, reversible or equilibrium, okay? Reversible or equilibrium process. And less than 0, which is not included, what is your guess? What you guess? Less than dSUniverse and dSUniverse, I am writing for you. dSUniverse less than 0 implies? Tell me. Yes, it is greater than 0 is irreversible, spontaneous. Is 0 reversible path? Then what remains? Impossible. Which is not possible. Like heat flow from low temperature to high temperature in an isolated system. So refers to impossibility. Refers to impossibility. Impossible path. That's it. And that's it, verily, that's it. Impossible path or impossibility. Okay? You right? Got this? Okay? dSUniverse less than 0. We'll discuss, start from this point next class. Means, okay, day after tomorrow. Thank you very much with this, okay? Okay, thank you. So with this, we have actually concluded today's class. Thank you.